Hi, folks. My name is Emily. I'm a machine learning specialist, solutions architect at Amazon Web Services. And today, we are going to learn about distributed hosting on AWS and especially with Amazon SageMaker. So, at this point in our journey, no doubt you've created a foundation model or you found a foundation model and you're trying to host this thing. So this session is all about diving deep into understanding what that is, why you would want to do it, how you can do it easily on AWS and on SageMaker. So let's dive in. All right. So first off, we're going to actually talk about different ways of building your foundation model applications. So if you're interested in working with foundation models, which I'm assuming you are, then first we'll recap different ways to build your applications. The reason we care about this is because we're going to work backwards from that to figure out different ways of hosting your models, especially on AWS. So these range from things like batch use cases to online use cases, serverless use cases, embedded use cases, things like that. So we'll learn how to host a distributed model, like once you've narrowed down your hosting choices and you're ready to just get to brass tacks, we're going to learn how to host a distributed model. So to take a model, park that model on multiple accelerators, multiple instances, and certainly multiple accelerators. Then we're going to look at some optimization techniques, so ways to improve the performance of that. Most of these are going to center around actually shrinking the size of the model, literally, so that it runs faster with a number of other techniques as well. Then we're going to close it out with a hands-on walkthrough of large model serving on AWS. In particular, we have a fully managed container, a large model inference container that you can use on SageMaker to easily get up and running. So let's check it out. All right, so let's say you've made it this far. You've picked your foundation model, you've evaluated it, you've tested it, you've run all the prompt engineering, you've run all the fine-tuning, you've done some pre-training, maybe you created a net new pre-trained model for fun. And now what are we going to do? So let's try and go find some customers. Let's put that foundation model in front of some people. So first off, let's think about your customers, right? Your end consumers. They might be using your website. They might be using your mobile app. They might be using some other unknown digital experience yet to be invented. And so in any case, these customers are going to be interacting with some type of client application, right? You've got some type of digital experience that you're exposing to these customers. And your goal in that phase is to simplify the customer experience. It's an important point. It's worth saying. You want to simplify the customer experience as much as possible. You want to minimize the amount of work that your customers have to do to understand your technical system, to use your technical system, to run it efficiently. And so the first life cycle here is like how your customers are interacting with your app, right? That's phase one. And then the second phase is sort of streamlining everything on the back end. So how your client application, which again can be your website, it can be your mobile device, how that interacts with the foundation model, how that stays up to date with the foundation model, how that prompts the foundation model, how that stylizes the content that comes out of it, how you run health checks, how you run fact checks, all things like this. And so different goal here, right? Because the goal is to streamline your development lifecycle. You want to get super fast and super good at just shipping new changes, at keeping your model nice and fresh, keeping the touch points between these systems on point and really clean without technical debts, so that you can innovate and so that you can add new technology really quickly. So at a high level, that's what we're trying to do. There are many different options for building foundation model applications, as we'll come to find out. Some foundation models are just strictly online, like you host a model on an endpoint with real-time inferencing, and people are just interacting with it. They click a button, for example, by typing in their prompt that invokes an API that hits the model, sends a response back right away. We call that online, right? The model is just interacting with the people in real time. A different type of application is offline, for example, such as running in batch. where maybe you store a number of records for something, and then you want to send those records to your model, run your model on those records, and then send the responses back. So that's a batch use case, also called an offline use case. Then there's also a queued use case where maybe you have your model hosted on some resources and you want to park a queue in front of that so that the requests sort of bundle up in this queue, and then as space becomes available, then they go and they get responded to, and then they come back. So a queue is an option. You can embed your model. So certainly embedded applications, which is similar to on-device, would be much more common in small foundation models. So for Stellar 1.3 billion parameter LLM that's like responding really well would be nice. Or yeah, that's probably a great option for a small chat, or a small stable diffusion model could also run nicely on device. And so those two are ways that you can actually take the content that is your foundation model and just put it directly embedded into your application code. This is recommended more for obviously low connectivity scenarios, where you're operating without connectivity to Wi-Fi, or where you just want a better, a faster customer experience, and so you just actually keep the model on the device. So that's an option. Then another option is serverless. So you can indeed, for some smaller models, compile those models, and then actually I've seen them converted into C++, and you can then put them in a Lambda function, believe it or not, to then operate at a much less expensive price point. And so each of these options have trade-offs. And there are trade-offs around latency, how quickly the responses will be. There are trade-offs around how expensive they're going to be. And there are trade-offs around how easy it is to lifecycle the entire model. And so you and your teams will need to figure out sort of which hosting option you're most interested in, and then go from there. So one online application is search. All right, so let's say I give you a search bar, I give you some search browser, you type in your search terms. I'm going to take your search terms and I'm going to use a model. Actually, I'm going to use a model to convert those search terms into something that's called an embedding. An embedding is a dense representation, which is a fancy way of saying a list. It's a long list of numbers that a model basically uses to understand context, right? So when we take any type of modality, be that vision, be that language, first we convert that into embeddings to then feed that into your neural network. And so we'll use a model to convert those search terms into embeddings. Then in step 2, I'm going to use some type of similarity algorithm, just like a k-nearest neighbors would do the job, combined with a vector store to actually find and retrieve my documents. The search and the similarity is going to operate at the embedding level. So I'll take my words for what's the weather like in Washington, D.C., for example, and I'll convert that into an embedding. And then in my similarity document store here, my vector store, I'm going to use like a KNN algorithm to go find a document that most closely relates to that. Then I'm going to retrieve that document. And then in step 3, I'll use another model to actually convert that answer into natural language. So to take the document, extract the relevant information from that document, and then convert that into a natural language answer that my consumer is going to like, that my customer will enjoy. So this whole process is called retrieval augmented generation. And it's using, as you can see, at least 2 models that are both hosted online. So these are online application examples where I'm getting sort of an immediate call and response to my customers, and I'm retrieving documents. Retrieving documents generally is a handy way to mitigate LLM hallucinations. So if I want to have a chat just about a couple PDFs or just about a couple documents, such as all of my consumer history, then retrieval augmented generation is a perfect way to do this. So that's an example of online applications. Here's an example of an offline application, which could be call center summarization. So in call center summarization, I might trigger this after the call completes. So if I want to do it offline, then I'll wait until after the call is done, and then I'll send out the transcripts. Alternatively, if I were doing an online application example for call centers, I would then host the model and be inferencing in real time. So just some differences there. So I'm going to trigger my job, and then I'm going to invoke a pipeline. So I'll trigger this pipeline sort of based on the action. I'll trigger a pipeline, which could be in Lambda or could be in any orchestration tooling. And then I'm going to point to my call center transcripts. So maybe I uploaded those to S3, and then using the upload to S3, I invoke a pipeline, probably the most common flow. And so I'll point to my call center transcripts, and then I'm going to run a batch job. So I'll spin up some instances, or just point to another LLM, maybe if the LLM is already serverless. And then I'm going to invoke the model with the transcripts. So then I'll take my transcripts, pop the transcripts into the prompt, and I'll say, dear LLM, give me a summary. And then I'll evaluate those responses and send them to my analyst teams. So this is a way to implement call center summarization using LLMs and using foundation models, notably in an offline fashion, right? Here we trigger this process after a call completes, invoking a pipeline, and sort of running some processes to prompt a model and then get responses back. All right, so how do we do this, you wonder? Now, I know this sounds very interesting, but literally when it comes to brass tacks, how am I going to take my model and put my model somewhere? So SageMaker has a really awesome model deployment stack. We have a lot of technology, a lot of capabilities that you can use to host your own models. And so this view sort of lets you see all of the things that are possible in SageMaker model deployment across different instances, CPU and GPU, accelerators, deep learning compilers and different model runtimes, a variety of model servers, such as TensorFlow, TorchServe, NVIDIA Triton, DJL, all sorts of things, and then frameworks on top of that. So the model server is sort of taking the responses and integrating those into a RESTful API. And then the framework is just implementing the model. So the framework is implementing the low-level model, which is then running just the forward pass through the neural network. And then SageMaker, of course, is managing the infrastructure for me, the actual instances. So in this, for the rest of the slides here, we're just going to look at real-time inferencing on SageMaker, using Hugging Face, and using the DJL serving library. So what do we need to host a model on SageMaker? So really I need three things. I need a model artifact, which is stored in my S3 bucket, and I'm going to want to tar zip that thing. So I have my model artifact stored in my bucket. I'm going to use an inferencing image that's hosted in a registry. So for example, I can bring my own inference.py scripts, but I might use an image that's hosted in ECR to easily get all of the packages that I need. And then, of course, I'm going to need some managed ML instances to actually provision this for me. One pro tip for you, the latest deep learning containers are a really great place that you can find scripts that run nicely. So basically, if you point to the latest deep learning container, it's much more likely to easily run your inferencing script. This is also true for training because we maintain really up-to-date deep learning containers. And so you can easily pick a deep learning container that matches your inferencing framework, such as PyTorch. And here we're going to look at a managed deep learning container for model hosting. So that's what we need. So the large model inference container on SageMaker starts with, again, a base Docker image. And then has the ability to work on different instances, so different accelerators, be that GPU, the Neuron SDK, or CPU. And so these are stored in the image. And then PyTorch runs on top of that. So PyTorch is going to point to those low-level frameworks. And then we'll use a distributed training framework on top of that. So the distributed training framework here is letting us shard our model over multiple GPUs. Commonly in this case, we're actually only going to use tensor and pipeline parallelism. Data parallelism is not needed because we're only doing a forward pass. So because we're only doing a forward pass through the neural nets, we're actually not doing any gradient optimizing at all because we're not training the parameters, we're just invoking them. So we don't need data parallel. Actually, we're just using tensor and pipeline parallelism. Great. And so we use this distributed framework to shard the layers of the neural network across multiple accelerators. And then we'll put all of this inside of a serving environment that lets us easily host that model and host distributed models. And so the large model inference container also includes just faster loading because the models are quite large. Some of the largest are actually multiple hundreds of gigs on disk. They're quite significant beasts. And so we want to use faster model loading to easily load those. And so this, again, is a managed container that you can use to host large models on SageMaker. So let's take a look at some of the latest. So these are available on GitHub. It is the AWS Deep Learning Container repository on GitHub. And so here you can just see, again, posted online, our different frameworks. So DJL serving with faster transformer, Hugging Face transformers, and Hugging Face accelerate. And this is the inference container, so these are for all inferencing. And then different accelerators, right? So GPU, neurons, latest versions of PyTorch, Python rather, more recent versions of Python, I should say, and then the example URL. And so when you're working with the deep learning containers, you can copy this URL. Actually, this URL is global. And so everyone is going to use this same address for the ECR image. So you're just going to literally copy this and then just update it based on the region that you're in. But the account ID is the same. So it's just a net copy. Then you can extend this thing. So once you are pointing to the deep learning containers, again, using the right region that you're in, and updating the container name, you can extend this container. This is, again, both for hosting and for training, and it's really helpful because you'll likely encounter some packages that aren't pip installable, that you actually need to write out some bash code for. Maybe it's a really gnarly install and a lot of really complex configs that you need. Docker is a great way to just build a net new image for yourself. This is true in hosting and for training, for notebooks as well, actually. And so this way you can easily, again, extend your pre-built container, package all of your programs into this container, and then interact with it. So this is a nice way to streamline your operations. All right, then let's just see if we can understand this thing. So we've got our model artifacts, our model weights sitting in S3. And then when we invoke this, when we spin up this instance, we're going to download the model from S3. So that gets downloaded to the model inferencing host, this inference endpoint through the model container, which is using Docker. This is then going to save the model on this local instance storage, in this case, some NVMe instance storage. Once this has been saved to disk, then we're going to load it, in this case using faster transformer, which optimizes the model for hosting. And then you see there are a number of options here. So Stable Diffusion, Deep Speed, generic Python scripts, Hugging Face Accelerate, and Transformers NeuronX. So a lot of different open source packages that you can use. Then we're going to load that model on multiple GPUs. So the large model inference container is really nice because it sort of handles a lot of the distribution for you. Again, because you're not doing any data parallelism, because we're not doing any backpropagation, it's easier to automate the partitioning of that, basically, for those reasons. And so we'll partition the model using those, and then that sort of result goes into the model server, which can then handle inference requests. So then inference requests interact with the model server, which then wraps the partitioned model, the model that's partitioned on multiple GPUs, and there you have it. That's distributed model hosting on SageMaker. But this is not the only thing. There are a number of optimizations for this, so ways that we can then improve our model to make it run faster, make the model smaller, and all of that improves our runtime. So if we start with a large model, then we'll likely use a model compilation and or model compression technique to just actually make the model physically smaller. So compilation will take the model and then compile it for appropriate GPUs. So it'll make it run faster and more optimally on a variety of GPUs. And then model compression has a similar effect, but operates in a couple different ways. So quantization actually changes the data representation. So you might have trained using FP16 or BF16, and then you might quantize down to integers. Actually, you might quantize down to int8, which has a smaller representation space. Pruning, you might just strictly remove some of the layers of the neural network, and you might perform distillation, where you start with a larger neural network, and then you run a teacher-student distillation process to then train this much smaller model. Model partitioning, model distribution we learned about, and then prompt engineering we've learned about as well. And so these are a number of ways that you can optimize your large models on SageMaker. And with that, let's check out the demo. So in this notebook, we are going to deploy a 175 billion parameter LLM. That's correct. This is a extremely large language model. This is an open source LLM built by Hugging Face during their big science project. This is known as Bloom. And so Bloom comes in a few different varieties. This is the largest at 175 billion parameters. And this notebook very cleanly wraps the end-to-end deployment. And so we're going to do this on SageMaker. So as before, we'll use the SageMaker example notebooks. In particular, this is a DJL DeepSpeed deployment notebook. And you have a QR code that you can use to get the link. Alternatively, if you're on a laptop or a desktop, you're welcome to just use the bit.ly. So let's check it out. All right, so as before, I'm in a SageMaker Studio domain, and here I have downloaded the notebook. So the notebook you'll see, and let's just go check this out over here. So the notebook is nice. You know what, let me use the bit.ly. So bit.ly, smnb 7 hosting. There we go. So this notebook is handy because it's extremely self-contained. I like that a lot about it. It doesn't use many other files. All of the files this notebook uses are actually just in the notebook itself. So you don't need many other artifacts. In addition, it also has this nice local mode option. So if you are running a notebook on a P4D machine, then you're welcome to run this here. So let's check this out. All right, so I'm in Studio, and here I'm running on a small CPU here. So this is the M5.large instance type. And let's take a look at this. So first we're going to just update Boto 3. and the AWS CLI and the SageMaker Python SDK. And then again, I'm going to go straight to the P4D hosted in the inference mode and not in the local mode, as I find that a little bit cleaner. But some people love to do locally. Local mode, if you're not aware, is a way to develop and test quickly for training jobs and for endpoints in SageMaker. And essentially you can add this parameter setting the mode to local, and then you can do a bit of local development there. All right, so we're going to grab a few artifacts here, and SageMaker likes the model to be in this tarball format, and so there's going to be a directory called code, and then this code directory is going to have this model.py, and that is the inference function that we're going to walk through, so you can see how to format your models for SageMaker inferencing. And then there's this serving.properties file as well. All right, so we'll do our SageMaker imports as usual. Got our execution role, session, bucket, etc. Then the model bucket, example files, the code prefix, HF, large model, DJL, and then the model prefix. And those are just folders in this bucket. And then the image URI. So the image URI, let's see where that comes from. Image URIs comes from the SageMaker Python SDK. And so this is an object that's going to let us just point to the base image that this endpoint is going to use. So image URIs.retrieve, we're going to provide it that framework name. So this is the DJL, or the Deep Java Library framework, which is nice for hosting large models. And in particular, this is a DeepSpeed version. There are many other distributed frameworks you can use for hosting a large model. This one just happens to use DeepSpeed. But you can also use Hugging Face Accelerate. You can use any number of new frameworks that have been developed. There's a lot of flexibility here. All right, so we're going to make our directory here. So this code Bloom 176. Oh, and this is the image URI, by the way. And so this is literally the address for that image in ECR. So here's our script. So from DJL Python, importing a couple objects, importing DeepSpeed. And then remember, the packages for this are already installed in this image. So because we're using this pre-built inferencing image for DJL, it has these base packages pre-installed, so there's no need to bring our own requirements.txt. If you do need to create your own container for this, then simply follow the steps to create a new container on SageMaker, notably by using a notebook instance, creating a new Docker container, pushing that to the Elastic Container Registry, and then you can use that for your hosting image. So here's our model.py, and we're importing DeepSpeed, Torch, Math, OS, and then from the Transformers library from Hugging Face, this autoconfig, the auto model for causal language modeling, and then the tokenizer. And then this load model function here is looking for the number of partitions. So remember, tensor parallelism, as we learned about in the session on distributed training, is a way to take your neural net, especially a layer in a neural network, and partition that across multiple accelerators. And so that would commonly be a multi-head attention block that is too big to fit on a single GPU, and so you need multiple GPUs or accelerators to partition that out. And so that's this parameter, actually, is the tensor parallel degree. And then the model location is the directory on the hosting instance where the checkpoints will be downloaded. So that's the model ID. And then the tokenizer, right, this should look very familiar. So the tokenizer is going to look in this model location. And so what this means is that you can, so here, what's happening is the name of the model is also being used as the name of a local directory on the hosting instance, where the model artifact will just sit. It will live there. And then we're pointing to that location from this auto tokenizer. And so we're reading from pre-trained that model location. And now we're going to construct a model. Interesting. With apparently with fake meta tensors, which will later be replaced during the DeepSpeed inference checkpoint load. Okay, interesting. So here we're going to define this false meta model, which will then update. So the model is this from this auto config, same as before, using BF16. And then the logging, and remember this just goes straight to CloudWatch so you can see what's happening. So starting DeepSpeed init with a tensor parallel degree of whatever this is going to be. And then we define the model. And the tensor parallel pre-sharded repos come with their own checkpoint config, which should be great. Then we'll define the model size here. In this case using int8, so that's quite aggressively quantized. Replacing a few objects here. And then setting the checkpoints. And then this is reading the checkpoints, which will then replace that base model. Okay, so you've got a function, right, load model. So this function load model is doing all of this for you. It's instantiating, it's initializing the tokenizer, and then is creating this DeepSpeed false model, which it then changes out by pointing to the checkpoint, and then just returns both the model and the tokenizer. And then this run inference function takes that model, takes the tokenizer, the new data on which you'd like to run inference, and the parameters. And then just set this, so we'll set the pad tokens, grab the inputs by performing tokenization on those inputs, just here, walking through those. And if it's a valid tensor, setting it to the device, and then calling generate. So then we're generating the input tokens, and here we're adding that. All right, so we've set the token to the device, which sends it to the GPU, then call model.generate. Then we get these outputs, and then we're going to run the outputs through the tokenizer one more time to get the natural language. And then the last process here is this handler that does some of this work for us. So it's using the global arguments, which is the model and the tokenizer, and then if it doesn't have those, it's going to try to load them. And then we'll get the data through the inputs, where these inputs are coming from the web server. So in this case, essentially this is coming from this serving.properties config. And so the web server, which is handling the API build out, is going to send you the data to basically through this function. So inputs, and then you'll just write that get as JSON, and you'll get your data. And then likely you set it as a JSON here. So then from that, we'll get the input sentence, and then we'll get the parameters, and then just try to run inference using everything as last time, using the model, the tokenizer, the input sentences, and the parameters. And then you'll get this output, hopefully, and then put the outputs in this new object, package that up, and then send it as a JSON. All right, and so that is your inferencing code. If you don't want to write your inferencing code, no worries. There are, of course, many examples that do this, and there are other sort of containers that have a slightly higher level approach where you can just send your model ID. So actually one of them is the Hugging Face. They have a lot of SageMaker example notebooks that are quite good. So let's see if we can find them. Yeah, from Phil Schmidt. So these are excellent. They're a really good source of examples. And there's one in particular for deploying that I was looking at recently, which is here. So this uses a new deep learning container that Hugging Face built for deploying large models. And what's nice about it and very straightforward is you just pass the model ID. So in this case, you really just send the model ID, such as here, to this framework, and then it's very easy to deploy. Now this is limited to a smaller number of models, so this is supported for these various model architectures, and so if your large language model is within this list of about 15, I'm exaggerating, list of about 10 models, then it should be quite easy because you simply point to it and then say .deploy, and that's quite straightforward. It's fun too, they actually added this little chat here that lets you like interact with it through a Gradio interface actually. Yeah, which looks like this. So then you can actually like chat with it in your notebook or locally, which is kind of fun. So that's nice. But let's go use our Bloom model. So, and I picked this one for you because I wanted you to see sort of this lower level of how you can build your own inferencing function. But if you don't want to do that, then the other notebooks are a good candidate path. And so let's keep going. So this is that serving.properties file, which is one way to write this. You can also just do write file, but that seems fine. And then just tarring the model archive, or tarring the model to produce the archive, uploading this local file to S3, so now it's out in S3. Optionally, you can add your VPC configs to this. And then we're going to create the model. So the model name here, which we can bring. And then we're going to use the, again, SageMaker Python SDK. So we'll create this model. We have this model name. The primary image is that inferencing URI that we got earlier. And then we have the Bloom model sitting in S3. And then we'll say create model. And that's this. All right. And then still using the SDK here, we'll give this endpoint config a name, and we'll create the endpoint config using the P4D. So a pretty large instance here that has 8 NVIDIA A100s on the P4D. And then we'll get the response. And so first we're creating this endpoint and the endpoint config rather. And then once the endpoint config is created, then we create the endpoint itself. And then once that's been created, the notebook essentially walks you through what we already looked at, which is some of the key points in that script to load the model from S3. And then there's a nice little wait function here. And then it shows status in service. And then we'll use Boto 3 actually to invoke the model. So then we'll use Boto 3 to invoke the endpoint. And we're going to send it this package, which is Amazon.com is the best. And then we have the parameters here. And then we get the result. All right, and let's see if we can do this for a different one. So maybe I'll try something like, today is the hottest day. And let's see what we get. So it takes a bit because it's quite a large model. So you're invoking the tensor parallelism here. And then here we go. It's quite an aggressive temperature, up to 1,000 degrees Fahrenheit. Goodness. Wow, that's quite aggressive. Obviously, here's an example of hallucination for you. Clearly, it's not 1,000 degrees Fahrenheit. Right now, it's about 84 degrees Fahrenheit. So 1,000 degrees would be impossible for life. But so in any case, then here's a slightly different example that uses different parameters. All right, and so with that, we learned how to use SageMaker to host large models using the deep learning containers, specifically for DJL. And then I also wanted to give a shout out to Phil Schmidt's awesome set of SageMaker example notebooks from Hugging Face. This is another way that you can deploy large models on SageMaker. So thank you. I hope you enjoyed this video, and you know, there's gonna be more coming. So hang out with me, and we'll get you some more content soon. Thanks.